what is usually called vector analysis or vector calculus. So first of all, yeah, the setting is the following. So now from in this section, we are going to restrict. We'll be dealing only with R2 and R3. So n equals 2 or 3. Now let's start with the notion of a vector field. So start with an open set in Rn where n equals 2 or 3. Actually, this definition I'm about to give is valid for any n. So a vector field on E is a well, at this point, I can put continuous C1, C2, or I mean, I may not even say anything at all. Basically, it's just a function. So is a function. Let me just not put any conditions. Is a function f from E to R3. So the way one thinks about it is at every, so this is your E. At every point of E, you are assigning a vector in R3. Well, why R3? I mean Rn, whatever n that I started with. At every point in E, you are assigning a vector which one thinks of as an arrow starting at that point and ending at some point. So this is a very simple and quick way of precisely capturing what one means by a vector field as we think about it in physics or engineering. It doesn't require too much theory to define this. Unlike for a differential form, it requires a bit more. So it's just a function from here to here. The main point is that this n is the same as the n that I started with. So open set in Rn, the vector field will be a map from to the same Rn. Usually, we require f to be at least C1. So continuously differentiable derivative. All right. So next, so let's write this. Actually, let me use capital F. That's what Rudin does. So f of x equal to, in terms of components, f1, as usual, I mean the same thing, fnx, which I can also write as f1x e1 plus fnx en. Hello, completely now. One minute.
Asha, yeah, I'm not going to go away. Come and take the phone, man. I kept it here. No, you just answer.
An executor is, you're right. So um, now the point is that associated to this, again, what I'm about to say is valid for all n. I'll tell you when exactly this n equals 2 or 3 is going to matter. Associated to f, we get a 1 form on E, so which I'll denote by lambda subscript f. So all you do is you just take the same functions, f1, f2, etc. Instead of e1, e2, en, you just put dx1, dx2, and so on. f1x dx1 plus fnx dxn. So if you have seen my notes in the notes that I put about linear algebraic interpretation of differential forms, this will turn out to be just the, see, you know that in any, if you have a vector space with an inner product or a vector space with a basis associated to each vector in the vector space, you get an element of the dual space. That is precisely what is going on here from that point of view. Well, if you have not seen my notes, then anyway, the definition of lambda f is simple enough. You just use the same coefficient functions and put dx1, dxn. Now comes the part about, so let's say if n equals 3, this will work only for this one. If n equals 3, not only do you get a 1 form, but you get a 2 form. We also get a 2 form, which we denote by omega subscript f equals f1 dy with dz. So here I'll use coordinates x, y, z rather than x1, x2, x3. f1 dy wedge dz plus f2 dz wedge dx plus f3 dx wedge dy. So, I mean, the point is that, oh, by the way, I should mention that here,
Sir,
yeah,
I am not sure. For some reason, I see your screen a little frozen. I don't see that two form.
oh, let me see.
Maybe it's just me. Oh, wait, it just loaded.
Ah, okay. Because I do see it on my laptop as well, not just the tablet. It's f1 dy wedge dz plus f2 dz. Now, what I wanted to say was that this is not in its standard form because, see, this dx, if you look at dx, dy, dz, these are the 1 forms. And a basis for 2 forms in terms of the standard forms would be dx wedge dy, then dx wedge dz, and then dy wedge dz, and that's it, right? x1, x2, x3. So you have to put the indices in increasing order. So dx wedge dy, so 1 dx1 wedge dx2, this would be dx1 wedge dx3, this would be dx2 wedge dx3. We have proved that these 3 will form I mean, anything can be written as, any form can be written as in terms linear combination of these where the coefficients are functions. This is not quite in that form because the first one is okay. Dy wedge dz is in the standard form. This is not in standard form, dz wedge dx. This is also okay. So in order to remember this, you just think of this dx, you write them in this sequentially like this. The forms we are working with are obtained by sort of cyclically going through them. So first you do dx wedge dy. I'll get dx wedge dy. Then you do this dy wedge dz. Then you come back dz wedge dx. So this would be cyclic. So this and then this and like this. So we get this. I mean, of course, yeah, so there is some choice involved here. For example, I could have defined another form. Instead of going this way, I could have put F2 dx wedge dz. That's also a valid 2 form. But this is rather, no, this is special, this way of writing it. So what is going on here is that secretly there is a map from omega 1e to omega 2e. And in fact, there will be a bijection like this. Now, this map is sort of hidden and Rudin doesn't even mention it. But if you study differential geometry and topology further, it's a very important map. This will, in higher dimensions also, there is such a map. It'll be from omega k to omega n minus k. There is some kind of what is called a duality going on in differential form. But in dimension 3, it's quite evident. If you do it this way, you get a 2 form from here to here. First of all, you have to notice that the dimension of this, well, both are infinite dimensional, but if you think in terms of this basis, this has n choose, well, here it's just 1 and 2. Anyway, so if I, more generally, there would be from omega ke, I'll just write it, for any n, there will be a bijection between these two things. There's some hidden map which is very important, but which I won't have time to go into, which will take this bijectively to this. Yeah, what I was about to say is, at least in terms of this dxi's, if you notice how many dxi1, dxi2, etc., which will make up a basis. Again, basis is not literally the right word because it's not a basis over real numbers. It's a, you have to use coefficient functions. This is an infinite dimensional vector space. So it doesn't have a finite basis. But if you use functions as coefficients, then the basis would have n choose k elements here. Here it would be n choose n minus k of the dxi's. But we know that this and this are the same. N choose k and n choose n minus k are the same. So there is, at least from that point of view, this sort of makes sense that there's a bijective correspondence between this and this. But it's not just by counting that one gets a map like this, the natural map. That is a different story, how one gets that. But here we have an explicit description of the map, which takes me, starting with a 1 form, I get a 2 form. And notice that I can go the other way around also. So if I have a 2 form, I can always write it like this, F1, this, and so on. I mean, if I write it in standard form, you will have dx wedge dz, but I can just flip it around. and write it in this form. So if I start with a 2 form, I can use the coefficient functions, get a 1 form, and then I can get a vector field as well, use the functions f1, f2, etc. So short is that there is a bijection. Therefore, so let's call if chi of E equal to set of C1 vector fields on E. Remember that this is just a fancy way of saying set of C1 maps from E to R3. So we have a bijection from this to omega 1 E to omega 2 E. Okay, so that's that. Next, let U equal to, let U be a C1 function on E. So U is a map from E to R. Then we have seen the gradient earlier. The gradient of U, which is defined to be D1U E1 plus D2U E2 plus D3U E3. This again, I don't need n equals 3. I can do it for gradient is defined for any n. Whenever I have a function, I get a gradient. This is in terms of coordinates D1U, D2U, D3U. Therefore, this gradient of U I can think of as a map from E to R3, i.e. gradient of U is a vector field on E. Now, if I want to say C1, if I want a C1 vector field, then I would be demanding that these partial derivatives are themselves C1. So that would mean that the original function should be at least C2, not C1 of E. Okay. If I just start with U in C1 of E, I know that partial derivatives are continuous. So gradient of U would be just a continuous vector field. So definition, let F be chi. So did I define chi of E to be C1 vector fields? Ah, yeah, C1 vector fields. The curl of F denoted by this symbol, I'll put it in quotation marks because it doesn't have any meaning. These individual terms here don't have any meaning other than what comes on the right hand side. So this thing is to be taken as one whole thing. Is D2 F3 minus D3 F2 E1 plus, well, you know the stuff, right? So it is D3 F1 minus D1 F3 E2 plus D1 F2 minus D2 F1 E3. Again, if you just start with a C1 vector field, since I've already taken derivatives, partial derivatives once, this new vector field that I'm getting, the curl of F, will be just continuous, that's all. These coefficients in brackets are just continuous functions. So I can't quite claim that curl of f is again in chi of E, but it's a vector field which is just continuous. The other thing is the divergence of f, which is denoted by nabla dot f. And this would be d1f, d1f1 plus d2f2 plus d3f2. The sum of the partial derivatives, appropriate partial derivatives. I'm just taking the first partial derivative of f1, etc. This again, the divergence of a vector field will make sense in any dimension. You carry over, extend, you can extend this definition to any dimension. This, however, is very special to dimension 3. So now let's see a nice link between this and our differential forms. So let U belong to C2. So C2E and G is C2 vector field on E. Since it's C2, I'm not using this chi of E notation. Chi of E is just C1. So I'm assuming something stronger here. Then if F equal to nabla U, so I started with U as just a function. I took, if I take its gradient, then curl of F equal to 0. All this stuff will be familiar to you. The proof is the more interesting part, not the statement. The statements are just usual 12 standard stuff. This is one thing. The other thing is that if F equal to curl of, no, not quite this. Okay. If F, actually this notation is a bit messed up. Here, right from here F is being used for a vector field. Oh yeah, that's okay. That's what we had been using all along. Okay. So if F is equal to curl of some other vector field, G, then divergence of F is 0. If E is C2 equivalent, I haven't defined this, I'll do so. I won't be able to prove this part. If F is C2 equivalent to a convex domain, convex open set.
Sir,
Yeah.
E is C2 equivalent, right?
Not that. E is C2 equivalent to a convex open set. Then A and B have converses. A prime is that, let's see what this is. So the A says that if F is the gradient, then its curl is 0. So the converse would be if the curl of F is 0, then F is the gradient of something. If curl of F is equal to 0, then there exists U C2 U from E to R with F equal to lambda U B prime. If F is the curl, then its divergence is 0. So we want to say that if divergence of F is 0, then F is the curl of something. Then there exists C2 vector field G on E with F equal to curl of G. So the point here is that these things are presented as, especially parts A and B, occur as somewhat isolated facts with no rhyme or reason. I mean, it's easy enough to check that they hold. But why these things happen? What is the meaning of these? Why is the curl 0 and why is the divergence 0 if F is curl and so on? Don't have natural interpretations when we are just stick to the realm of vector fields and classical vector analysis. But when we translate these statements to differential forms, then it becomes extremely natural, as you will soon see. Well, it would have become very natural had I done the section before this, the section about closed and exact forms. I skipped that. If one had that, what I'm about to say will be extremely natural. But even without that, one can sort of see it more clearly why these statements are true. So the point is, both for all these A, B, and their converses, the idea is to work with the one form, or analog. Given a vector field, we get a one form. So let's translate these statements to one forms and see what happens. One form, and there's also a two form involved. So the proof hinges on the following statement. F equal to nabla U if and only if lambda F equal to du. I won't prove this. These are nice, simple exercises. There's nothing, no subtlety involved here. It just involves checking the definition. What is du and so on. So F equal to nabla U if and only if this happens. And then the curl of F is 0 if and only if d lambda F is equal to 0 and what else, right? And then F equal to the curl of something if and only if omega, now comes the two form, omega, the two form associated with F equal to d lambda G. Actually, I could have, instead of writing these two separately, I can just, after the second one just follows from the third one, right? See, if we have this F equal to nabla G if and only if omega F equal to this, if the curl is 0, so if the left hand side is 0, then if F is 0, omega F will also be 0. Therefore, this. Actually, this implies this. Keep this in mind. This is the strongest statement, the third one. And the divergence of F is 0 if and only if d omega F is equal to 0. So if you see the pattern here, what is going on? Notice that the RHS is a statement of the form eta equal to d alpha or d eta equal to 0. Every one of them is of this type. That we are saying that some form is d of some other form. That is one kind of statement. The other statement is d of a given form is 0. In the first case, I'm saying lambda f is d of u. So it's of this type. The second statement is d lambda f is 0. That's of this type. Omega is d of something. It's of this type. D omega f is 0 is of this type. So these two conditions, that's what the entire previous section is all about. These two conditions. These two conditions have a very important. So I'll just make a definition. For details, see previous section in Rudin. So the definition is that, and this again is valid in any dimension, any form of any degree and so on. There is nothing to, these definitions have nothing to do with dimension 3. If eta equal to d alpha, so eta is some k form on an open set E in Rn, and alpha is a k minus 1 form. Then eta is said to be an exact form. If d eta is equal to 0, then eta is said to be closed form. Now, the first observation one makes is that this if a form is exact, then it is closed. Exact implies closed, because if eta is d alpha, d eta would be d of d alpha, and we know that d squared is 0. So the set of exact forms is a subset of the set of closed forms. In fact, it's easy to check that these are vector spaces as well. So this vector space is a subspace of this, and the starting point of the link between differential forms and topology is precisely the study of not quite these spaces by themselves are not that important, exact and the space of exact forms and space of closed forms. What is important is sort of the quotient space, closed forms modulo exact forms. So if you start looking for which closed forms are not exact, that has to do with what is called the topology of the underlying space. So for example, so here's the theorem which I'll anyway need proved and ruled in, but I won't prove it. Just a simple integration actually. So if E is convex, and again this is in Rn, nothing specific to R3. Convex open set in Rn, then the converse is true. Here we are saying that exact forms are closed, but if E is convex, then closed forms are exact. I.e., given any eta in omega ke with d eta equal to 0, there exists alpha in omega k minus 1 e such that d alpha equal to eta. Now you will get an inkling of why what the so far the role of E was not that important in all our considerations. E was just an open set. We never paid much attention to. We never put any other condition on E. Here we have put a very strong condition that E is convex. For these considerations, closed, when is a closed form exact, etc. This the everything hinges on the nature of E actually, as it turns out. Give another example. Let E equal to R2 minus the origin. Then there is a closed one form on E which is not exact. This of course is not convex, E R2 minus 0. But actually the convexity is not the right thing, but the point is it somehow depends on the set, underlying open set, whether this closed forms are exact or not. And we have seen this form. Does anyone recall, anyone meaning there are exactly 5 of you, does anyone recall what this one form is? On R2 minus 0, we had dealt with this before, which is close but not exact. I think we had even shown that, maybe we had not shown this, but we had talked about a specific one form on R2 minus 0. Do you remember what that is? Or was it given as an exercise? Because the one we had talked about, yeah, we, let's see. No, there was something we had. Well, maybe it was in the homework. Let me quickly see. Ah, yeah, right. This was in the, yeah, this was part of your homework. had assigned it a home. The one form is x dy, x divided by x squared plus y squared. This function times dy minus y divided by x squared plus y squared dx. This one form, if you just take partial derivatives appropriately and check, d omega will be 0. And well, right, d omega will be 0. On the other hand, how does one show that it's not, how does one show that omega is not equal to d eta? Now, omega is a one form. So eta, if at all it is d eta, eta should be a 0 form. In other words, a function for any C2 function f from R2 minus 0 to R. Have you done this homework at all or not? If you have done this homework, you should be able to answer this immediately. This is a very important homework. I mean, all these questions, whatever is in Rudin's exercises, they are very important things. So how does one show that this is not d eta for anything? Well, this is usually quite difficult to prove. In this case, it's somewhat, it's easy to check that d of something is 0. It's just a computation. But to show that it cannot be written like d of any eta is usually tricky. But in this case, so I don't want eta here, I want an f. So I want omega is not df. So anyway, I won't do this, but I'll just leave. I'll just tell you that you please go back and check exercise 21. This is problem 21 on page 292. Okay, and the way one shows that it is not. Let me tell you what the punchline here is. The way one sees that it's not df is that you take, let see, one forms, you take this capital phi from the one simplex to R2 minus 0. Phi of t is cos 2 pi t sine 2 pi t. It's not, of course, it's not an affine simplex. It's just the circle. The image is a circle. And then you integrate, basically, if omega over phi, if it is d of something, it should be the same as df over phi. Then you explicitly compute that this will actually give you 2 pi using the definition of integral of a differential form over a K surface. You compute this. And here what you observe is that, again, using you compute this as well, you'll end up getting this one is just f of phi1 minus f of phi0, which will be 0. So that would be a contradiction. So the point is that df integrated on, and in fact in okay, so that's that. So the point is that, in fact, it's not so important. One can show that the circle is not important. If you integrate it on any closed curve which encloses this missing point, the hole is somehow should be inside. If the hole is inside this closed curve, then again the left hand side will be non-zero, right hand side will be zero. That's what will happen. But with the circle, you can directly do it and you'll see this. Okay, so now, but if the E is convex, then the statement is true. So with this in hand, all the stuff about actually,
So,
yeah,
um, this R2 minus 0 and the
yeah,
last comment that you made about any curve enclosing this point,
yeah,
mm, this makes it look like it's not the convexity that's as important as the connectedness of E.
yeah. That is the point. In fact, that is true. What I was about to say next is precisely that point.
Oh, okay.
So the next point is that, let's say it's a corollary of the theorem about convex sets, that we say if that, let's call it U is C2 equivalent to a convex set, everything open in Rn. Again, this is not specific to n equals 2 or 3. Uh, if there exists some phi from U to E, which is bijective, phi is C2 and phi inverse is also C2. This will, of course, imply that the moment phi inverse is assumed to be differentiable, it will follow from the chain rule that the derivative of phi is non-singular at every point. That's a small consequence of this. So C2 equivalence means that there is a bijective map which is C2 and the inverse should also be C2. If this happens, if U is as above, then in any closed form, same conclusion as for a convex set holds for U. Any closed form in U is exact. So this gives quite a bit of freedom. See, if you start with a convex set, the nicest convex set one can think of as a ball. But you can heavily distort it by this C2 equivalence, the bijective map. So you can just distort it any way you like. You just have to keep track of the fact that this should be 1-to-1 and on 2, and the inverse should be differentiable. Inverse should be differentiable. The inverse is being differentiable is hard to interpret geometrically, but at least the 1-to-1 part is clear enough. You just distort it, stretch it, pull it, or do whatever you want. You will get, so this is E. Actually, my map is going in the opposite way, as in from the definition. So this should be phi inverse in that notation. So this U need not be convex at all. But the main point is, as you said, is that this E does not have any holes or missing points. And this same thing holds for U. It may look very sort of distorted, but the inside is all filled up in some sense. There are no holes. And that no holes or not is the key property for this, whether every form is closed, every closed form is exact or not. Now, the proof of this corollary is easy, because basically you just translate every statement to E. So you start with a form here, omega, let's say d omega is 0. So this is phi. Now I want to use information about E. So what do I do? Any suggestions? How do I? So
Pull back.
obviously, pull back. Pull back by phi or phi inverse?
Well, you want to go to E, right? So
Yeah,
phi in phi inverse, right?
phi inverse. The pullback map goes in the opposite direction to the original map. Phi inverse goes from E to here. Pullback will take me from U to E. So you do omega with that earlier notation, it would be this, right? So you can pull back omega to get a form here. Now, will it continue to be closed? D of this. We already seen that pullback operation commutes with D. So this is the same as D omega phi inverse. And this is 0. So you do get a closed form on E, the convex set. And applying the theorem to E and to this form, the pullback form, therefore there exists alpha on E, some form of some degree, such that the pullback form omega phi inverse is equal to D alpha. So here I have this is equal to D alpha. Now you just transport this information back to U. So you pull back alpha to U. Now this time I'll use phi. Consider alpha phi on U. Just claim a simple claim that omega equal to what is it? D alpha phi. And how does one see this? Well, again, one uses this, that's all. So this is to see this. Just take actually here my earlier notation of pullbacks rather than Rudin's notation. Remember I had this notation that if F is from U to V, the pullback was denoted by F star. That notation is more handy rather than using F as a subscript. Just take pullbacks. Okay, so this anyway, I'll leave it to you. So this basically you want to see that omega is D alpha phi, right? So, and this is D alpha phi is D of alpha and then phi. Not quite like this. No, have I written it correctly? Omega. So what I got was I got this equal to this. Oh, right. So then I take phi of this. Yeah, this is correct. This is d alpha phi. Yeah, this is correct. What I wrote is correct. That's fine. D of alpha phi. But omega, the idea is to write omega equal to phi inverse and then phi. Because remember, we had proved that omega is t equal to omega is t, this equation. So if you use that, then I can write this as like this. So this is this equation that we want is equivalent to saying that this equal to this. So is this true? Well, we already know that this equal to this. So therefore, if you take one more pullback, this is we get this. So that's it. We're done. So you can just, this is standard trick. If something is equivalent to something else, you just transport it there and so on. So now let me continue with that. Unfortunately, yeah, I can't go back. So I'll just finish the proof of this quickly. So remember the gradient f equal to this, if and only if lambda f equal to du, that's one thing. Then lambda cross f equal to 0, if and only if d lambda f 0, f equal to nabla cross g, if and only if omega f equal to d lambda g, nabla dot f equal to and only if d omega f equal to 0. So if you look at the first statement, so the first statement A was if f equal to nabla u, then nabla cross f equal to 0. Well, in terms of differential forms, this is the same thing as saying that if lambda f equal to du, then d lambda f is equal to 0, right? And that of course is true because d lambda f is d of du, and we know that d squared is 0. So that's done. And what about the converse? Oh, by the way, before the converse, b is also the same thing. If f equal to this cross this, then nabla, this is 0. If and only if the two form is d of something, then d of the two form is 0. Again, if the two form is d of a one form, then d of the two form is d squared of that one form, and so it's 0. What about the converse? Well, converse is also the same thing. A prime. Converse would be saying that, for example, for the first one, if the curl is 0, then it's a gradient. Would be the same thing as saying that if d lambda f is 0, then lambda f is equal to du. But that is precisely what that we know that no meaning. I just quoted it. I didn't prove it. That happens on a domain which is on an open set C2 equivalent to a convex set. So the converses follow from the theorem and corollary about convex open sets and closed and exact forms. So that is that, okay? So the point is that all this somewhat random facts about curl and divergence, etc., everything is just a matter of, from the modern viewpoint, it's just about when certain differential forms are closed and when they're exact. That's it. What is not evident is the way we got this. By the way, this you should check this. So this is homework. That these two are equivalent. When you're checking this, you will see why omega f is defined the way it is, not in the standard form, but that cyclic permutation of dx, dy, dz. But even this explanation is still only part of the story. For example, that as I told you, how one can get a one form is clear enough. You can do it in any dimension. From a vector field, you get a one form. But how did we get this two form? Requires some more theory, and it can be done in higher dimensions also. Right. Um, so what? I'm a bit puzzled. So why are there only two people in this thing? I'm just noticing that there are only two people in the audience.
It is possible that one, we are nearing the end of the course, and two, these recordings are available online. So maybe some of them might have.
But
They
this is
might
the
have.
most difficult part of the course. I mean, what I'm about to say will be the hardest part in a way. Not because, I mean, as I've been repeatedly saying, it's not the actual mathematical calculations, but the concepts and so on, these are somewhat abstract. Anyway, it's up to you, up to them rather. So it's everything is will be online. I hope people there are in the midsem there were some people who are perilously close to failing. Quite a few, in fact. That's what I'm worried about. But anyway, nothing can be done about it. What can I do? So now this, yeah, at least it took care of one part of the story. Unfortunately, this it will. And I was thinking of posting some more lectures, but if seeing the diminished audience now, if I, on top of the class, if I post lectures, it will be and ask you questions about that in the exam, it might not end out well. It might not turn out well. That's my worry.
Uh,
But, uh,
Sir, the exam apart, if there is more
hmm.
material that you want to cover, then I think all of us would be okay with more recorded lectures showing up. We should probably set some boundaries as to what part will be there in the exam and what part we can consider as supplementary or something.
Well, there is that. Okay, what I'll do is the best way to do it would be, I guess, I'll see how much I can cover day after tomorrow. I definitely will not be able to cover whatever I had in mind. So I'll supplement that with one or two lectures. And if it is okay, I mean, okay in the sense, if it makes sense to break off at certain point, I might not ask questions about the recorded lectures, but if I feel it depends on how much I'm able to cover. If I feel that I've covered enough, then I might ask questions about the recorded lectures also. Okay. If the recorded lectures end up just being some filling in the details of various proofs, then I might think. So what I'll do is, see, the main thing is that I want to emphasize in this, especially the last part, Stokes theorem part. It's not just some abstract concepts and proving random theorems. you can actually, you should be able to work out specific cases and do simple examples. So I plan to give some more homeworks, in fact, emphasizing this part. Rudins already has some stuff. But for instance, this part, problem 21, which I had already assigned, I'm surprised that none of you recalled this. That one form on R2 minus 0. This is a very important example, actually. This one. This is not the only one form, but this is the easiest one, which is of. And this was an assigned homework. This kind of thing you should know. More than proofs of theorems. Yeah, let me emphasize that. The proofs of theorems are somewhat long and sometimes a bit subtle, but that is one part of the story. But more than that, you should be able to work with differential forms, integrals, and so on in actual practice in simple cases. There's no point knowing the proof of a theorem, Stokes theorem, and not being able to even compute a simple integral. Okay. So let's stop here, and I'll continue giving homeworks. As to when you can submit it, we'll see. But more than submitting it, this material that this homework problems you should do, because, well, obviously to learn the subject, and then also from your exam point of view. Okay. So let's stop here.
All right.
Okay. Thanks. Bye.
Bye, sir.